These are the answers to the Chapter 17 practice quiz, starting with the multiple choice questions. Number 1. The dissociation of the weak acid HF, hydrofluoric acid, in water is represented by the equation above. We're looking for the effect on the percent ionization of HF in two separate experiments. First, adding distilled water to a sample of HF, and second, adding a solution of potassium fluoride to a sample of HF. Let's talk about the distilled water first. Back in Chapter 16, this information is on pages 672 and 673, we learned that there was an inverse relationship between the concentration of a weak acid and the percent ionization. So when a weak acid is diluted, it causes a shift in the direction of the products, and that will increase the percent ionization. So adding water or diluting a weak acid will increase the percent ionization. Now, on the other hand, according to the common ion effect, if we add a solution that contains fluoride ions, it will shift the equilibrium toward the left. So a common ion is going to decrease the percent ionization. So the correct answer to this question is C, because diluting the acid will increase the percent ionization, but adding fluoride ions will decrease the percent ionization. In number 2, we are given some information about lactic acid, which is a weak acid, and we're trying to figure out which of the following mixtures would make a buffer solution. Now, a buffer solution should contain a weak acid and its conjugate base. So for a weak acid and the conjugate base, we're looking for a mixture of both lactic acid and the lactate ion. So the problem with choices C and D is that they are a mixture of a weak acid and a strong acid. That's not going to create a buffer. So the answer is either A or B. Now, when you add hydroxide to lactic acid, you can produce the lactate ion. So the problem with choice B is that based on the moles, all of the lactic acid would be completely converted into the lactate ion. So you're not going to have that buffer solution. You're not going to have a mixture of both lactic acid and lactate. So the correct answer is A, because based on the information in terms of moles, only half of the lactic acid molecules are converted to lactate, so we get that mixture of both lactic acid and its conjugate base. In number 3, we are given a buffer which contains both acetic acid and sodium acetate, and we are asked to explain why, after adding a strong acid to the buffer, the pH did not change. So on page 708, we have a situation with a buffer in which either a strong base or a strong acid are added to the buffer, and the concentrations don't change very much. They just change slightly, but we keep that ratio pretty much the same. So here, when we add a strong acid, the conjugate base, F minus in this case, is going to react to keep that ratio relatively the same. So here in this case, the strong acid is being added, so it's going to be the acetate that reacts with the strong acid to produce acetic acid. So that's going to keep that ratio relatively the same. In number 4, we have a buffer that contains both hypochlorous acid and sodium hypochlorite. And now we're adding a strong base to this buffer, and there's going to be a slight increase in the pH. So the final pH will be a little bit higher than 7.5, and in terms of the species that's present in greater concentration, once hypochlorous acid reacts with the strong base, the hydroxide, that will cause the concentration of the hypochlorite ion to increase. So the correct answer is D. All right, questions 5 through 8 refer to the diagram. This is a pH titration curve, and we're starting with a weak acid, and we're going to be titrating it with a strong base. Let's talk about the different concentrations of various species throughout all the stages of this titration. If we begin the titration with a weak acid, HA, then there's mostly HA in solution at point Q before the titration begins. Now, anywhere in this region, before the halfway point, there should be more HA than A minus. At halfway to the equivalence point, there should be an equal concentration of HA and A minus. In this region, after the halfway point but before the equivalence point, there's going to be a greater concentration of A minus than HA. And when we actually reach the equivalence point, there's just mostly A minus in solution. And then beyond the equivalence point, we now have some excess hydroxide ions. So question 5 says, at point R in the titration, which of the following has the highest concentration? At that point, there's going to be more HA than A minus. So the correct answer is A. Number 6, if we are at point U in the titration, we're beyond the equivalence point, we're looking for excess hydroxide ions. So the correct answer is B. In number 7, when the concentration of A minus is twice as much as HA, we must be past the halfway point. So the correct answer to this question is C, point T. And in number 8, now we're going to do a molarity calculation, trying to determine what is the concentration of the weak acid HA. So what do we know? We know that the molarity of the sodium hydroxide solution is 0.1 molar. We know that the volume of the sodium hydroxide solution, which is the titrant required to reach the equivalence point, is 40 milliliters, and we get that from the graph. We don't know the molarity of the weak acid, but we know that they said the volume of that acid was 50 milliliters. So because of the 1-to-1 mole ratio between the sodium hydroxide and the acid in this titration, we can say that M times V, molarity times volume for the acid, is equal to M times V, molarity times volume for the base. We plug in everything we know, and we solve for the molarity of the acid. 40 times 0.1 is 4, and 4 divided by 50 is 0.08. So the correct answer to this question is either A or B. Now what happened was they used an indicator that changes color slightly past the equivalence point. So let's say that instead of stopping at 40 milliliters, they might have stopped at around 42 milliliters. So what that's going to do is cause the concentration, the calculated concentration of acid, to be slightly higher than 0.08. So correct answer is B. Questions 9 through 11 refer to an experiment in which lithium reacted with water, it produced hydrogen gas, and then a solution was used to titrate a monoprotic acid. So this titration curve looks familiar to us. We've seen an example of weak acid, strong base. We know that the pH at the equivalence point is greater than 7. So this looks like a traditional weak acid, strong base titration. Now, when you're at the halfway point, halfway to the equivalence point, the concentration of the weak acid is equal to the concentration of the conjugate base, and pH equals pKa. Looks like the equivalence point was reached at around 25 milliliters. So half of 25 is about 12.5. That puts the pH at approximately 5. So therefore the pKa of our acid is about 5. Number 10 is asking which indicator would be the best choice for determining the endpoint. Remember that you want the indicator to go through its color change as close to the equivalence point as possible. So you want the color change to be anywhere along the rapid rise portion of the curve? Well, the rapid rise portion of the curve in this case is around 8 to 10. So therefore, thymol blue would be the best choice of indicator. In number 11, we know that lithium reacts with water, and it's going to produce a solution that is a strong base. So therefore, choice A cannot be correct because lithium is reacting with an acid solution. We know that lithium reacts with water to produce hydroxide ions, but it should be a solution. There should not be any precipitate. So we can eliminate choices C and D. The correct answer is B. And if we go back to our textbook, back in chapter 7, here on page 269, they're showing you that the alkali metals react with water to produce hydrogen gas and a solution of an alkali metal hydroxide. All right, this is number 12. We're going to do a similar calculation we saw earlier with molarity times volume for the acid equals molarity times volume for the base. Now we know the molarity of the base. It's 0.2. We don't know the molarity of the acid. The volume of the acid that they used every single time was 100 milliliters, and the volume of the base varies. As you can see, the choices A, B, C, and D. So I'm picking 75 milliliters and see what that does. Now 2 times 75 is 150, so 0.2 times 75 is 15. If we solve for the molarity of the acid, we get 15 divided by 100, and 0.15 does not fall within the range of 0.2 and 0.3 as described in this problem. So the correct answer is not B. Let's go ahead and try C. Now we're going to have 2 times 115, which would be 230, but this is 0.2 times 115, so it's 23. Divide that by 100, and now the molarity of the acid is 0.23, which does fall in that range, so the correct answer is C. Questions 13 and 14 refer to a strong base, strong acid titration. We have sodium hydroxide and hydrochloric acid, and the products of the reaction are just sodium chloride and water. The pH is 7 at the equivalence point because sodium chloride is a neutral salt. If the pH is 7, that means that the concentration of H plus and the concentration of OH minus is 1 times 10 to the negative 7 at point R. We're looking for ions that have a concentration greater than 0.01, so it could not be H plus or OH minus. All we have is salt, NaCl, and water. So the correct answer for number 13 is A. Number 14. What if they used 1 molar hydrochloric acid as the titrant instead of 0.1 molar hydrochloric acid? Well, that's the original curve. If we used a solution of hydrochloric acid that is 10 times more concentrated, you're going to have so many more moles of H plus ions that your equivalence point will happen much more rapidly. So the curve still has the same equivalence point at 7, but you're going to eventually go past the equivalence point with a more concentrated acid, so the pH beyond the equivalence point is going to be lower than in the original curve. So it's not going to change the initial pH. That's because you start with a strong base. It's not going to change the equivalence point because you're still producing a neutral salt. But past the equivalence point, you have much higher concentration of acid, so a much lower pH. Equation number 1 in this question is FeF2, so iron Roman numeral 2 fluoride, dissociating to produce iron 2 ions and fluoride ions. And we have a K1 2 times 10 to the negative 6. So that solid is not very soluble in water. Then we have the reverse of a weak acid, so we're kind of combining fluoride and H plus to produce hydrofluoric acid, and that is a large value of K because the reverse is small. Then we have a reaction involving the FeF2 reacting with acid. How can we add the first two equations together to get us the third equation? We're going to need to take that second equation and multiply it by 2. That's going to cause the value of K to be squared, so raised to the second power. And when we multiply the two values of K together, when you add equations together, you multiply the K values, we'll have a product that gives us 2 for our answer. And since that is greater than 1, the reaction should be favorable. So K3 is greater than 1 because we're multiplying 2 times 10 to the negative 6 times 1 times 10 to the third squared. Number 16 shows us the exothermic dissolution of magnesium hydroxide in water. And because it's exothermic, we can imagine that on the right side of the equation, we have plus heat. Which of the following changes will increase the solubility of magnesium hydroxide? Well, increasing the temperature is like you're adding heat. And according to Le Chatelier's principle, when you raise the temperature, the reaction will shift in the endothermic direction. In this case, that would cause a shift toward the left. If we add either hydroxide ions or magnesium ions, that's the common ion effect, that would cause a shift to the left as well. So why is the correct answer B? Remember, this is on page 729, that when you have a salt that contains an anion that acts like a base, then the solubility will increase as the solution becomes more acidic. So when you lower the pH and make the solution more acidic, you are going to remove hydroxide ions, and that will shift the equilibrium toward the right, making it more soluble. All right, number 17, this is a pretty easy question because we know that the greater the value of the KSP, the higher the solubility. So we can eliminate choices C and D because their values for KSP are rather small. Now what I did, even though we're not supposed to use a calculator, is I went ahead and used a calculator to show you the concentration of chloride for lead chloride and for copper Roman numeral 1 chloride. And I'll make a point with the information once I do that. So let's take a look. So here is our KSP for lead chloride. So concentration of lead times concentration of chloride squared. And then for the KSP for copper chloride, just concentration of copper times concentration of chloride. So with the lead chloride, I have X and 2X based on the 1 to 2 stoichiometry, the mole ratio. And for the copper chloride, it's just X and X. So when I solve for X with the lead chloride, I get 0.014, which is my concentration of lead, and 0.028, which is my concentration of chloride. Now you can't do that math in your head, but you might have assumed that chloride was going to be a larger number coming from the lead chloride calculation, whereas from the copper chloride calculation, it's going to be roughly 10 to the minus 3 or 10 to the minus 4. And you can see that that is a much smaller value. So your answer to this question was really not based on hard math. It was based on knowing that the KSP value for lead chloride had the highest value. So therefore, it's going to contain the highest concentration of chloride ions. All right, number 18. We are given 1 liter of a solution that contains silver nitrate and lead nitrate. The concentration of silver is 0.02 moles per liter. The concentration of lead is 0.001 moles per liter. And to this solution, we're adding a sample of potassium sulfate, which may or may not precipitate either of these salts. So silver sulfate and lead sulfate, we have KSP values given. How much sulfate is added is 0.001, and that's in a 1 liter solution. So we know the concentration of sulfate is 0.001. We're going to do a Q calculation and decide if Q is larger or smaller than KSP for each of these salts. Starting with the silver sulfate. There is our expression for KSP, 0.02 squared times 0.001. Now this is without a calculator. So 0.02 can be written as 2 times 10 to the minus 2. And when you square that number, you get 4 times 10 to the negative 4. When you multiply by 10 to the negative 3, Q is equal to 4 times 10 to the negative 7, which, as you can see, is less than the value of KSP, so a precipitate of silver sulfate will not form. Now on to the calculation for lead sulfate. We have 0.001 times 0.001. That's going to give us 1 times 10 to the negative 6, which, as you can see, is larger than the KSP value. So a precipitate will form for lead sulfate. Question 19 deals with the common ion effect as it applies to the solubility of calcium fluoride. We're going to be adding additional fluoride ions to a saturated solution of calcium fluoride. So therefore, the additional fluoride ions will shift the equilibrium toward the left, and that's going to cause the concentration of calcium ions to decrease, and it's going to produce additional solid calcium fluoride. So it increases the mass of solid calcium fluoride. So the correct answer is B. And now on to the free response questions. Number 1, we have 2 solutions. We have a 1 molar solution of hydrofluoric acid, and we have a 0.8 molar solution of sodium fluoride. Let's start with the pH calculation for the solution of hydrofluoric acid. Ka is equal to H plus times F minus over HF. We know the concentration of HF is 1 molar, but we don't know the concentrations of H plus and F minus, so we'll call them X and X. When we solve for X, that gives us the concentration of H plus, and it works out to be 0.026. And by the way, the simplifying assumption here is valid. I did the quadratic equation for this and I still got 0.026. The negative log of that number is 1.59, so that is our pH for solution 1. Now solution 2 is a base. It's sodium fluoride. So let's see what the Kb value is for the fluoride ion. The Kb is the Kw divided by the Ka, and we do this math to give us 1.5 times 10 to the negative 11. Let's use the Kb to solve for the pH for solution 2. So here's our expression, our Kb expression with fluoride on the bottom and hydroxide and HF on top. The concentration of the fluoride is 0.8 moles per liter. We go ahead and solve for X, and that gives us the concentration of hydroxide. We take the negative log of this number, and that gives us the pOH. We do 14 minus the pOH, so our pH of this sodium fluoride solution is 8.54. Now, when we combine solutions 1 and 2, we're going to turn 500 milliliters plus 500 milliliters. That's going to create 1 liter of solution. So I have in 500 milliliters of 1 molar HF, I have half a mole of HF that's now dissolved in 1 liter. So I've got 0.5 molar for my concentration of HF, and I have 0.4 molar for my concentration of sodium fluoride. Notice that the original concentrations were merely cut in half because we doubled the volume. 500 plus 500 is 1,000, so the new concentrations of HF and sodium fluoride are 0.5 and 0.4. So solution 3, we can do the pH either by starting with the Ka expression, plugging in 0.4 and 0.5 where they go, and solving for H+. We can negative log that and we get a pH of 3.07, or you could have used the Henderson-Hasselbalch equation, so the negative log of the Ka plus the log of A minus over HA, in this case 0.4 over 0.5, and we still get a value of 3.07 either way. So the 2 components of our buffer, that's what we have right now. We have a buffer because we have a weak acid and its conjugate base. The 2 components are HF and F minus. So which one of those buffer components is going to react with a strong acid? Well, an acid has to react with a base, so F- reacts with the H+ ions to produce HF. If you chose to write hydronium instead of H+, then you would have F- reacting with hydronium to produce HF and water. Either way, that reaction would be correct. All right, what's the new concentration of HF and F- if we add 4 milliliters of a 10 molar HCl solution? So there's our original concentrations of HF and F-. Now 4 milliliters of 10 molar HCl would give us 0.04 moles of H+ ions. Since the F- is reacting with the H+ to produce HF, the concentration of F- is going to go down, and the concentration of HF is going to go up. Well, by how much? By 0.04, because we have exactly 1 liter. So our new concentration of HF is not 0.5, but rather 0.54. And the concentration of F- is not 0.4, but rather 0.36. So F- went down, HF went up a little bit. So let's see if our new pH is going to be pretty close to around 3. That's what we had before. We're going to use the Henderson-Hasselbalch equation this time. So now I'm putting in that math into my calculator, and I get a pH of 2.99. So the pH did go down, but just slightly, because we have a good buffer. All right, number 2. We're starting with propanoic acid, and we're titrating it with potassium hydroxide. The balanced net ionic equation for this reaction between a weak acid, propanoic acid, and potassium hydroxide, a strong base, I'm going to write the propanoic acid formula, but I'm only going to write hydroxide for my potassium hydroxide since potassium is going to be a spectator ion. Then I get water, but I also get the propanoate conjugate base, which has a charge of -1. So here's our overall equation. And now let's talk about the titration experiment. So our volume of acid is 25.0 milliliters. Our concentration of acid is, well, we don't know what that is yet. Our volume of base that was used to reach the equivalence point, we can get that from the graph. So that's 35 milliliters. And our concentration of potassium hydroxide is 0.5 moles per liter. So we're going to figure out the concentration of propanoic acid. That's a pretty easy calculation. That's an m times v equals m times v kind of a calculation. All right, next question is, what's the Ka for propanoic acid? Now you know that the halfway point, which in this case is around 17.5, the pH equals the pKa at halfway to the equivalence point, and that's around a pH of 5. So because pH equals pKa at the halfway point, and the pH is around 5, that means that our Ka is 1 times 10 to the -5. All right, now we're going to calculate the moles of potassium hydroxide that reacted. That's volume times molarity equals moles. So 0.035 liters times 0.5 moles per liter, 0.0175 moles of potassium hydroxide was used. And because of the 1-to-1 mole ratio between the base and the acid, I also have 0.0175 moles of propanoic acid that was consumed in this experiment. So for the concentration of the propanoic acid, it's going to be 0.0175 moles of acid divided by the volume which they gave us. That's 25 milliliters, or 0.025 liters. So my concentration of propanoic acid is 0.70 moles per liter. Now we have to circle 2 of the following chemical substances that are present at the highest concentration in the solution at the equivalence point. Now in the beginning of the titration, we had a lot of propanoic acid, the molecules that had not been neutralized yet. At the halfway point, we had an equal concentration of both propanoic acid and propanoate, the conjugate base. But now we're at the equivalence point. So pretty much all of the propanoic acid has been neutralized by the potassium hydroxide, which is a strong base. So what do we have? We have water. we have the propanoate ion, and then we have the potassium ions. Now we don't have extra hydronium, we don't have extra hydroxide because we're exactly at the equivalence point. We have the salt that was produced in this neutralization reaction between a strong base and a weak acid. And that salt is potassium propanoate. So those two ions are present in highest concentration. Now what is the more important of these two ions? Which one of these ions actually has an effect on the pH of the solution? Well, that's the propanoate ion because it is a conjugate base. So because the propanoate ion is the conjugate base, it's going to behave as a base, and this equation will justify why the pH is greater than 7 at the equivalence point. We're going to produce the original propanoic acid molecule, but we also produce hydroxide ions, and that's why the pH is higher than 7 at the equivalence point. This is not a neutral salt, this is a basic salt. All right, is methyl red going to be a good indicator for this titration? Well, recall, this is back on page 721 in your book, that when you have a weak acid with a strong base and you get a pH higher than 7 at the equivalence point, phenolphthalein is good, which changes color somewhere around 8 to 10. But methyl red is bad because it changes color roughly around 4 to 6, and you would stop your titration before reaching the equivalence point. You would stop too soon. So the question is asked, would methyl red be appropriate? And the answer is no. It would not be appropriate because it finishes its color change around pH 6, which would cause the scientist to stop the titration before the equivalence point is reached. All right, question 3, we're talking about magnesium hydroxide. Magnesium hydroxide has one magnesium, which has a charge of +2. It has two hydroxide ions, and the charge on hydroxide is -1. So there is your KSP expression, concentration of magnesium times concentration of hydroxide squared. In part B, we are given the pH of a saturated solution of magnesium hydroxide. So clearly we're focusing on the hydroxide ion to figure out what that is going to tell us from the pH. pH is 10.52. That means that the pOH is 3.48, and the concentration of hydroxide is 10 to the minus 3.48. So 3.3 times 10 to the -4 moles per liter, that is our concentration of hydroxide. Now there is a 1 to 2 ratio between magnesium and hydroxide, so the magnesium concentration is half as much as the hydroxide concentration. So 1.7 times 10 to the -4, I now have the concentration of both magnesium and hydroxide, which means I can plug those numbers in to the KSP expression and calculate the value of KSP. So 1.7 times 10 to the -4 times 3.3 times 10 to the -4 squared. My KSP, based on these numbers, is 1.9 times 10 to the -11. Now you might have gotten 1.8 times 10 to the -11 if you left the numbers in your calculator without rounding. That's fine. All right, what do we do with this KSP? We're going to compare Q to KSP and decide, is a precipitate going to form when these two solutions are combined together? We have magnesium nitrate and we have sodium hydroxide. So what's the concentration of magnesium in the final solution? And what's the concentration of hydroxide in the final solution? Well, if I do volume times molarity equals moles, and then moles divided by total volume is molarity, I get a magnesium concentration of 2 times 10 to the -4, which, as you can see, is exactly half as much as the original concentration, because we're doubling the volume, so we're cutting the concentration in half. So in a similar way, I get a concentration of hydroxide, which is 1.5 times 10 to the -4, exactly half of the original hydroxide concentration, because we're doubling the volume and we're cutting the concentration in half. Let's take these numbers and plug them into the KSP expression. This is our Q. When we do this math, we get 4.5 times 10 to the negative 12. Now, is this higher or lower than the calculated value of KSP? Well, it is lower. So since Q is less than KSP, a precipitate of magnesium hydroxide will not form. Okay, well that wraps up the answers and explanations to the Chapter 17 practice quiz. I hope that was helpful. Thanks for watching and good luck studying.